Good morning. Let's see. Okay, so we will start in 3 minutes. Okay, so let's start. Okay, so today we will finish the discussion on predicate calculus, and then we will also be starting and finishing the topic about rules of inference. Okay, so let us continue about the predicate calculus. So here we talk about something called binding variables. So let's take a look of this thing. Okay, this kind of looks like a mathematical expression. So inside here, x plus y is equal to 1. We see that it is what? It is a propositional function. So in this function, when the value of x and the value of y, when they are both fixed, then we know that it becomes a proposition. So x plus y is equal to 1 is a propositional function with two variables. But now, suppose that we have added there exists x here. So there exists x now is used to quantify this particular propositional function. So in that case, the whole thing is there exists x such that x plus y is equal to 1. And now we will see that when the value of y is known, then the whole thing will become a proposition. So this thing is actually now becoming a propositional function with just one variable. The variable is y. And then you can also see that, let's say if I have another quantifier, let's say added at the beginning, let's say for every y, for all y, just like this one, for all y added at the beginning, then in this time, the x value, the y value, we are no knowing that what we are going to look for. So in this case, the whole thing will now become a proposition. So why is it true? So here, a simple rule is that when we have a propositional function and when there is a quantifier of a certain variable added to the expression, then we will say that the variable here is bound. So here in this expression, there exists x is added here so that the variable x is now bound. On the other hand, the variable y is not bound, so it is called free. And when all the variables are bound, then in that case, the propositional function becomes a proposition. Okay, so free means that I am freely changing the value at will, but then bound means that I've already fixed how to look at the particular variable. So a more closer look of what has happened. So the for every y is applied to the whole thing. There exists x plus y is equal to 1. Recall that this is a propositional function on y. So in that case, for every y, a propositional function on y is a proposition. And then there exists x when it is applied to this one. This is a propositional function on x and y. But when there exists x is applied to this one, it becomes a propositional function on y. And then we also talk about the scope of a quantifier. So the scope, so how far this quantifier for every y is affecting the expression. So this part is the scope of for every y. This part is the scope for every y. And how about there exists x? There exists x. This is the scope of there exists x. Okay. So the concept of scope is just how far it is affecting, and then it appears as well when you are studying some kind of programming language like C or C++. So if you look at this, so this is a very long expression. So we have for every y not equal to 0. This is a shorthand notation, but basically it is for every y. Then the scope of this one is only affecting up to this point. And then we have another part here. So we have there exists x here, and then the scope of there exists x is here. Now we will see that this part is a proposition because every variable is bound. And similarly, this part is also a proposition. So we have a proposition and another proposition. So this is also a proposition. Now notice that the scope of y here only applies to this part. So in that sense, we can just use the same variable name x here, and then it is still safe because we know that this x that we are talking here is not the same as this x that we are talking. So we will be able to make sure that this part and this part are two separate things. But on the other hand, if we want to have this x to be affecting this x and this x at the same time, then what should we do? Then in that case, we should make a big bracket here somehow. But then we cannot have for every x and there exists x at the same time because a variable can only be bound in one way. Okay, and then also we will see that the order of quantifiers will be very important. So exchanging the order may give you a different meaning of the expression. So for instance, let's assume that x and y, they are both talking about integers, so their domain are integers. So let's see, what does that mean? Okay, so here it says that for every y there exists x such that x plus y is equal to 1. So it means that, so we can actually read it from left to right and then use our common sense to understand what it means. So it says that for every integer y that you can imagine, there is always some x that you can find so that the result of x plus y is equal to 1. Now for this one, this is actually something true. For instance, if I imagine a y which is equal to 17, then I can find some x which is like negative 16, so minus 16, such that the result of x plus y will now become 1. And if I think about another integer, let's say y is equal to 0, then I can think about some x here. Let's say x is equal to 1, such that x plus y is equal to 1. So here, actually, for any possible y that you can imagine, once you have imagined the value of y, I can then choose some x such that I make this part true. So in that case, the whole thing is actually true. But on the other hand, let's exchange these two parts. Let's exchange the two quantifiers here. So suppose that there exists x is now put here. So we have there exists x for every y, x plus y is equal to 1. So here, what does it say? It is saying that we can find a very special value x such that no matter what y that you imagine, the value of x plus y is going to be equal to 1. Now we will see that this x is impossible. Yeah, there is no x such that this is true. Because if x works for a certain y, then this x will not work for another y. So there is no something like a universal x that is going to be okay for to be applied on any y such that x plus y is equal to 1. So we will see that this expression using our understanding is false. So the first expression, the first proposition is true, the second proposition is false. So this gives us an example that exchanging the order of quantifiers will have different meaning. But then there are two special cases, okay? Okay, if all the quantifiers are universal quantifiers, then it is okay. And the other case is if all the quantifiers are existential quantifiers, it is also okay. So for instance, there exists x, there exists y, such that x plus y is equal to 1 will have the same meaning as there exists y, there exists x, such that x plus y is equal to 1. So how can we show this? Okay, so this one is easy to show by saying that anything that makes this true will make the second part true. And similarly, anything that makes the second part true will make the first part true. So in that case, the two propositions will have to be true under the same conditions. So in that case, they are equivalent. Okay, and then in the class, so we have gone through a couple of exercises about English translation. So it will be very useful for you to try it out yourself and check for the class recording for the details. So here, so let's look at this as a certain example that we have discussed. So here it says that every student in this class has studied calculus. Now suppose that QX denotes the expression x has studied calculus, but here the domain here is also very simple. Let's say x is concerning of about all students in this class. Then in that case, this expression is very easy. So this expression will be something like for every x, q of x. Is that okay? But on the other hand, suppose that we now have a restricted domain. Suppose that x is now not just all students in this class, but then it consists of all students in NTHU. Then in that case, the domain is now changed. So in that case, we will need to have another expression for this translation. So in that case, we will need to use the idea of restricted domain and give corrections. So this is an easy example. And later we have some other examples. Yeah, something like this. So for instance, this one says some fierce creatures do not drink coffee. And then we have QX to represent X is a fierce creature, and then RX to represent X drinks coffee, and then so how can we do the translation? So we will now have QX and RX related. And then now this one is even more complicated. So here it says that if a person is a female and is a parent, then this person is someone's mother. So of course, this looks like something that is true. So we have expression like f of x to represent x is a female, p of x, now I use p for parent, x is a parent, and mxy is x is a mother of y. So here we will have something like an expression that involves fx, px, and mxy. So try it out by yourself. And then another one. Now this one is, I think, is a very complicated case. Okay, so it says that every person has exactly one best friend. So we will just need to have the concept of bxy to say that y is the best friend of x. So how can we express this or translate this into a proposition with this bxy as its propositional function inside? So to solve this, so let us first forget about this part exactly. So just say that everyone has a best friend. So for any x, there will be someone, there will be y, such that y is the best friend of x. So this is having the same meaning, right? So you see that you are using that exists, and then you are using for every. And after you can solve every person has one best friend, then the next part is how do you translate the whole thing to add one more concept about exactly. So exactly one best friend, it seems that if someone is already my best friend, then nobody other than that person can be my best friend. So in that case, you need to have two concepts. So a person needs to have certain one as a best friend, and for any other person that is not that person, then it cannot be a best friend. So if you can have these two combined together, then that means that every person will have exactly one best friend. And then there is another example. So this is rather simple, so don't worry. And then there are also a lot of cases where we are actually using this translation in mathematical arguments. So for instance, we can talk about the sum of two positive integers is always positive. So how can we express it using this kind of notation? So for instance, yeah, so here is actually it is not just say that the sum of a particular positive integer x and a particular positive integer y. It really says that if I have any positive integer x and if I have any positive integer y, then their sum must be positive. So it involves any, or for every. The second part is similar. So we have for every real number that we can imagine except 0, then we can always find some other real number, or maybe some real number. It could be the same, okay? But the product of these two is equal to 1. So how can we express them in logical expressions? And then this one is a very strange one. So you can, this is doing the opposite. So suppose that I have already told you the meaning of fxy. So it means that x is a friend of y. Then I have a very long thing here. So what does that mean? Okay, so this is very strange. So you can try to figure out what is the meaning of this part. Okay, and then, yeah, so we have talked about logical equivalences of propositions. And now we have logical equivalences of propositions that has a quantifier inside. So for instance, we have just mentioned that the ordering of the quantifier will be okay if they are all of the same type. So there exists x, there exists y. I can exchange this so that I can have this proposition is always having the same truth value as this proposition. So they are equivalent. And similarly, for every, I can exchange it. So this one. So these two are two examples of logical equivalences that involves quantifiers. And another one that I want to introduce, it is the De Morgan's law when we have quantifiers. So De Morgan's law is something like we have for every x px, if I want to negate it, if I want to make the opposite of it, then what we need to do is we change for every into there exists, and we change the original propositional function to its negated form, and that's it. So here, so this is actually following our logic. So here it says that it is not true that every x will make px true. So what does that mean? So it must mean that you can find a counter example of x such that px is not true. So if this happens for every x, px is not true. So if this happens, then that means that it must have some x such that not px is going to happen. Now the negation of there exists x, px will be changing, like there exists, you change it to for every, and then px you change it to the negation of px. Okay, so again the same as in our daily understanding. So if it is not true that there exists some x that makes px true, then it must mean that for every x that you can imagine, px cannot be true. So this one and this one, they are exactly the same. Okay, so this is the De Morgan's law. Okay, so this is about the what I want to talk about this predicate calculus. So let's move on to another more exciting topic, the rules of inference. So when we have talked about the rules of inference, then we are getting close to proving things. So okay, so let's see. Okay, so this is the new set of slides, rules of inference. Okay, so in this set of slides, we will talk about what is meant by a mathematical argument, and we will give some rules that helps us to deduce something can be true or must be true based on some certain facts that we are already know. Okay, so in mathematics, an argument is a sequence of propositions followed by a proposition. And then the sequence of proposition at the first part is called the premises, and then the final one is called the conclusion. And then not all arguments are important. Most important arguments are valid arguments. The valid argument is something that makes sense. So it means that suppose that all the premises are true, then we must have the conclusion to be true. So for instance, let's see this example. So in this example, there are two premises. The first one, it says that if it rains, I drive to school. And then the second part says it rains. Now suppose that this is really my habit. These are something that is true. So whenever it rains, I will drive to school. And now it is really raining. Then using our common understanding, then we will see that we can give a conclusion that I will now drive to school. Yeah, this makes sense, right? Okay, so at this moment, we will see that this is talking about applying logic in our daily understanding. And then in the previous example, the arguments actually, they belong to this particular form. So P stands for it rains, and then Q stands for I drive to school. So in the previous arguments, or in the previous case, then we will have the first part is of the form P implies Q. It rains, then I drive to school. And then the second part is it rains, which is P. And then we have a conclusion that I drive to school will be correct. Indeed, we can have a different argument, but but let's say it is of the same structure, something like if I am hungry, I will go to have pizza, something like this. And now it says that I am hungry. Then what can we draw as a conclusion? So we will see that I will have pizza, right? So if I am hungry, I will have pizza. And then now I am hungry. So that means that I will have pizza, right? So it is also of this form. I'm hungry, then I will have pizza. I'm hungry now, so I will have pizza. So in this particular case, then we will see that this form is very useful. no matter what kind of proposition P that we plug in here, no matter what kind of proposition Q that we plug in here, as long as we know P implies Q is true, and we also know that P is true, then we can draw a conclusion that Q is true. So in such a case, we call this a valid argument form. And today we will look at a bunch of valid argument forms that we use, okay? Okay, and then what exactly does a valid argument form require? So because by a definition, a valid argument form must have the case that whenever the premises are true, then the conclusion will be true. So what does that mean? So it means that when P1, P2, P3, and Pk, they are n together, is true. That means that it is true. It implies Q, this thing is always true. So if this happens, then it is a valid argument form. Oh, recall this word tautology. Tautology means always true. So whenever the conjunction, the end of all the premises implies the conclusion, this whole thing is a tautology, then it will be a valid argument form. As mentioned, we will talk about a lot of valid argument forms today, and because they are very commonly used, we will call them rules, and they are called rules of inference. So they are very easy thing because we are using them every day. So you won't find it something like amazing, okay? But on the other hand, this is really amazing because you can teach a computer to think based on these rules of inference. Now, so the first one is what we have just mentioned. We have P implies Q, then the conclusion is Q. Now notice that the ordering of the premise doesn't matter because in any case, premise conclusion, we will require that all the premises are true to derive the conclusion. So the ordering of the premises, how we mention them, doesn't matter, okay? Now this is working, we have explained this, and then this is called the modus ponens, okay? Now this is a, I think, Latin word, and then roughly meaning is method of affirming. Method of proving things is to be true. So you have P implies Q. So in that sense, positively, I will tell you that Q is true. Now, don't worry about how to memorize these words. So in your exams, it is going to be open book. So you don't need to memorize this exactly, but it will be good if you find it easy to memorize them, but it is still okay, perfect okay that you can recall how to find this name later in your exam, okay? And then the other one is called modus tollens. So in modus tollens, the premises are a little bit different. So we will still have P implies Q, but then this time I have not Q. Then in that case, I will have the conclusion of not P. Something like, if I have eaten this cake, then my mouth will be dirty. And here, it turns out that my mouth is rather clean now. It's clean. So what does that mean? It means that I didn't eat the cake. Okay? So I deny that I have eaten the cake by saying that my mouth is not dirty. Okay? So eat cake implies dirty, but then I'm not dirty. So that means that I didn't eat the cake. So it is called the method of denying, or modus tollens. Okay? So how to prove it to be true? Easy. You have this one. You have this one. Let's check the n together. And let's say whenever we n them together, whether it implies not P is always true. Okay, so we can check whether this is a valid argument form based on the truth table. But you will see that it is true, right? By our daily understanding. Okay, the next one is the hypothetical syllogism, and it is also very, very useful daily. So suppose that I know that if P happens, then Q will happen, and then if Q happens, then R will happen. Let's say we know that this is true, and also this is also true. Then the combined effect will be, we know that when P happens, then R must happen. Okay? So something like Yeah, I think it is a rather easy example, right? And then the other one is called disjunctive syllogism. So it says that I know that P or Q will be true, but then now I told you that not P is true, so that means that P is false. Then what do you know? We know that Q must happen. Q is going to be true. Okay, the next one is addition. Addition looks rather useless, but then if you want to teach your computer to think, then this may be required. So here, let's say the premise is just P. I know that P is happening. Then I know that P or Q must happen. Yeah, because this is already happening. So P or Q will be true always. And simplification here it means that suppose that I know P and Q is true. Then I know that P has to be true. Reason, P and Q to be true already implies P is true and also Q is true. So we can just say one part because it is already known that both are true already based on the premise. So in that case, we can just make a conclusion that P is true, although we also know that Q is true. So we call this a simplification. Now conjunction is also straightforward. Suppose that I know P is true, I know that Q is true, then I know that P and Q has to be true. Now this resolution is a little bit strange if you look at it at the first glance, but then it have an easy explanation. So let's see. Suppose that I know P or Q is true. Suppose that I know that not P or R is true. Then I will know that Q or R is true. Oh, rather strange. So the P disappeared. The reason here is that, okay, if we put these two things together, P or Q and not P or R, together, suppose that we know that they are both true, but then in one case, we know that in one of the case, it must be P or not P, it is false. I don't know, maybe this is false or maybe this is false. So what does that mean? It means that one part here has to be true because we need this one to be true and we need this one to be true. So we will see that at least one of these Q or R has to be true. They can both be true, but then at the bottom line, one of them has to be true. Okay, the next one is the universal instantiation. Suppose that I know that for every xpx is true, then we can make a conclusion. This is not just a conclusion, this is actually an English translation. We can write down that PC is true for any C that we can think of. And the universal generalization is the opposite. So suppose that we know that PC is true for any C, any arbitrary C that we put in, PC will be true. Then in that case, we can make a shorthand expression to write for every xpx. Yeah, they are the same meaning. And we also have existential instantiation. So there exists xpx means that we can find some element C such that Px is true. It's not okay for every element C, but we know that some element C, it is already okay. Some means that one of them, some of them. And similarly, suppose that we know that PC is true for some element C, then instead of writing the long English sentence like this, then we will see that we can make a conclusion. There exists xpx. Okay, so we have a bunch of examples here. So we will talk about this in the class, but let's see if we can get an interesting example here with you together. Okay, so let's go through with one example here. This one, let's say we go through example 2 here together. So here in this example, I have 3 facts that we know. So the first one, it says that if you send me an email, then I will finish my program. So let's say I'm a programmer and you are my boss. If you send me an email talking about this program, then I will finish my program. But on the other hand, if you, my boss, do not send me an email, then okay, good. I will do nothing and then I can go to sleep early. And then the third one is, if I go to sleep early, then I will wake up next morning feeling refreshed. Okay, so let's say these are 3 facts. And somehow, can we conclude this one? If I do not finish my program, okay, then that means that I will wake up refreshed. It is rather strange, but it is something that is true, okay. So strangely, if I do not finish my program, then that means that I will wake up refreshed in the next morning. Okay, so how do we interpret this? So for instance, let's say we use this variable to simplify our discussion. P represents you send me an email, Q represents I finish my program, R is I go to sleep early, and then S is I wake up refreshed. So in the previous three facts, the first one says, if you send me an email, then I will finish my program. So P implies Q. And then the next one is, if you do not send me an email, then I will sleep early. And then the third part is, if I go to sleep early, then I will wake up refreshed. And then we hope to prove that the conclusion, when I do not finish my program, then I will wake up refreshed. So how can we get? So we have these three as the premises, and then this is a conclusion. So let's see how we can show this is true. So we can show this is true, of course, by using a truth table, assuming that whenever these things are true, what are the special cases? And then we'll hope to see that for all the cases that makes all three true, then this one will be true. But then you will see that we have PQRS, then the table will be very large. So on the other hand, we can use logical reasoning, mathematical arguments to help us. So this is how we can show. So the idea here is that we want to have a bunch of things here so that in the end, we get this one as our conclusion, the target conclusion as our conclusion. Okay. So first of all, so there are many ways of showing this. I'm just giving one example. So don't worry if you are using your own proof. So there's no unique way of showing things. So here, the first one is we start with this premise, P implies Q. Yeah, so P implies Q is a premise, so we can use. And then the next one, I'm claiming that not Q implies S is also true. It says that it is the contrapositive of 1. Yeah, because 1 is now true, then the contrapositive, this one, contrapositive of 1, something wrong. What is contrapositive of 1? Let me see. There seems to be a typo here. So it looks like this is not S. Sorry, this is not S. There is a typo here. This is not P. Okay, so not Q implies not P. I'm sorry about this mistake here. So P implies Q is the same as not Q implies not P. So this is not P. And after that, we know that not P implies R is a premise. Is that okay? So in that case, not Q implies not P, and not P implies R. We will have not Q implies R. So this is the hypothetical syllogism by using statement 2 and statement 3. And then we also have R implies S. So we have 4 here. We know. So notice that everything that we write it down here, we will make sure that it is true. Either it is because it is a premise which is assumed to be true, or it is derived from some other premises or some other statement using the rules of inference to make sure that it is true. So 4 is now true, and then 5 is a premise which is true. So when this is true, when 4 is true, and when 5 is true, then we know that 6 is true because it is simply the I'm really sorry about so many mistakes here. I will try to make corrections here. So this is not modus ponens of 4 and 5. Sorry. So this is again the hypothetical syllogism of 4 and 5. Is that okay? So yeah, I'm sorry about the mistake. But anyway, this is the point. Yeah, the point is what we need to. So let's do another example. I'm really sorry about this. Let's do another. So there are many mistakes here. Okay. Okay, so how about this one? Okay, so this one is a little bit more complicated. So suppose that we know 2 facts. So suppose that a student in this class has not read the book. And then also we know that everyone in this class passed the first exam. So here we want to conclude that someone who passed the first exam has not read the book. So for our understanding, it is easy, really easy. Yeah, because we have we are thinking, we are doing this kind of logical thing daily. But then, how do we prove it using pen and paper? Because this is important for a computer to understand why this is correct. So let's do the simplification here. Suppose that Cx, so C stands for class. So suppose Cx says that X is a student in this class. Bx says that X has read the book. And then Px says that X passed the first exam. So the previous two statements, this one, statement 1, and statement 2 can be translated into this one. So it says that there exists a student such that this student is very special. This student is in the class, but then this student has not read the book. So we can find a certain student such that this student is in the class at the same time and has not read the book. So this is the first statement. The second statement is, it says that for every student in the class that we can imagine, then the student has passed the exam. So for every X, whenever X is in this class, then it implies that X has passed the exam. So this is about the second one. And then we hope to get this as our conclusion. It says that there exists someone who has passed the exam and has not read the book at the same time. So how can we do this? Okay, so let's see. Okay. So the first one is there exists X, Cx, and not Bx here. It is our premise, so we can write it down safely because it is true as a premise. And now, using 1, we can talk about existential instantiation. So here, because there exists some X that makes this true, so let us just find out such an X. Let's call this X A. Okay. So Ca and not Ba for some particular A. And at this moment, the value of A is fixed for some particular A that has this particular proposition to be true. And then from this one, this part and this part, we can use simplification to just keep Ca here. Okay, at this point, let us switch our focus to another premise. So this time, we have for every X, Cx implies Px. Now this is a premise, so we can write it down, it is true. Now because this is about for every, so no matter what X that we talk about, it is going to be true. So we can take out the A that we have already fixed here in step 2, so that we know that Ca implies Pa is also true, because it is true for any Cx implies Pa. So this part is true for any X. So not just any X, but also a particular X, which is, we set it as A. Now we have 3, we have 5. So this time we can have modus ponens by 3 and 5 so that we can know that Pa is already correct. And similarly, from statement 2, we can also use simplification to get not Ba. 6 and 7 now can be combined by using conjunction. And now it says that for that particular A, Pa and not Ba is true. So this time we can change this back into, from this English sentence, back into the existential form. So we can write it down as there exists X such that Px and not Bx is true. So we are starting from our premise here, knowing them to be true, and we have a bunch of reasonings here written down so that in the end, we can get our conclusion. Now notice that in a full proof here, we will need to write down the reasons. All of them. Let's say if you are using a very smart computer, the smart computer can really understand that your proof is correct, can verify, can check whether your proof is correct. And how to find this kind of proof could be difficult, but checking is easy. Okay, so I have a final question. So a final remark here. So this is a story extracted from the Sherlock Holmes story. Okay, so Sherlock Holmes is written by Sir Arthur Conan Doyle. So if you are a big fan of the comic book Conan, which is about the detective Conan, a young kid, then his name is picked from this author's name, Conan. So in a book called Silver Blaze, which is about a horse, okay, then we have the following conversation between Sherlock Holmes and a policeman. So Sherlock Holmes is a private detective, and the policeman is in charge of a kind of someone being killed. So here, this is the conversation from Sherlock Holmes before he is going to leave home for another business. Okay, so the policeman asked, okay, so asked Sherlock Holmes, is there any point to which you would wish to draw my attention before you leave? Then Sherlock Holmes says, to the curious incident of the dog in the night time. And then Gregory, the policeman, says, the dog did nothing in the night time. And then Sherlock Holmes says, this was the curious incident. So what was in the nighttime, that part? So that night, it is someone being killed or someone being murdered. But then in that particular night, the dog in the house did nothing. So what is so special about this? Okay, so Sherlock Holmes wants to point out that if there is a stranger breaking into the house doing something bad, then probably the dog must be aware of, and then it will bark. But then at that night time, the dog did nothing. So we will then conclude that there is no some unusual person, some stranger breaking into the house to do bad things. So what are we doing here? So we are actually saying something like, if there is a stranger, then the dog will bark. And then the dog did not bark. So we can have a conclusion that there is no stranger. So we are actually using modus tollens here, the method of denying here. Okay, so yeah, that's all. So although we are going through many slides, so I have missed out a lot of examples here. So please try it and then see if you can work out the correct answer, and check the details through the OCW recording. And then if you still have questions, yeah, please send us emails. Okay, so that's all for today. And then yeah, we have also sent already the homework one. Yeah, also try it. And then we will meet again next Monday during the tutorial. Okay, thank you. Thank you very much.